Hi, and welcome to this lesson on analyzing velocity time graphs. In this lesson, we'll see how we can use velocity time graphs to find velocity or time. Then we'll talk about how to find distance and displacement. And thirdly, how we can use velocity time graphs to find the acceleration of an object. Let's start with velocity or time. And we'll start with the example. Let's say our question is, what is the velocity at a time equal to 4.0 seconds. In order to answer this question, we'll first identify at what point on our x-axis is 4 seconds. Well, that's right here. So at the time equal to 4 second mark, we need to then locate where our graph is. So our graph is indicating to us that the velocity is equal to 1.0 meters per second, read directly off the graph. If we ask what's the velocity at a time equal to 7 seconds, at the 7 second mark right here, we see that the velocity is about 1.75 meters per second. Finally, if we ask what's the velocity at 17 seconds, here's the 17 second mark. The velocity looks like it's close to, not quite 1.5, maybe 1.4 meters per second. So to calculate or to find velocity once you're given the time, you simply have to read it off the graph. Similarly, when it comes to finding a time for a given velocity, we'll read it directly off the graph. We use the example now. What is the time that the object was moving negative 1.5 meters per second. So there's our question. What is the time the object was moving negative 1.5 meters per second? We'll work a little bit differently. This time we look for our negative 1.5 meter per second mark on our y-axis, and we try and locate where our graph is, and we see that that was at a time of 17 seconds. So when time is equal to 17.0 seconds, our velocity is negative 1.5. Similarly, if we wanted to know what time the object was moving 1.0 meters per second, we'll just find the 1.0 meter per second mark on our y-axis, and we trace along and see it was moving at that rate at 4.0 seconds, but it is also moving at that rate at about the 13.5 second mark. So that question would have two answers. Let's move along. If we want to find the distance and displacement from a velocity time graph, we have to ask ourselves about the area of the graph. That's the indication of both of those. For this example, let's take a look at the whole trip from 0 to 18 seconds. And I'll break it into distance on this side, and I'll do my work for displacement on this side so we can compare and contrast the two ways that we find these two different values. We'll start with this graph, and the first shape that we see on this graph. We're asking about the area. It's the area defined by the graph itself. So I'll highlight the first shape, or the first segment of the trip. That goes from 0 to 8 seconds. And the shape of the graph gives us one side of our, or the graph gives us one side of our shape, and the other side, or one of the other sides, will be the x-axis itself. So when we put this together, we see that the first shape is a triangle. The second part of the trip is indicated by this blue shape. Here's our graph. Here's our x-axis for the same time period. And then we just complete our shape by drawing these vertical lines down. The next shape is indicated by this part of the graph here. I'm going to end at the 0 mark. You'll see why that is later on. So I'll highlight this one in black. And so we have this black triangle right here. And finally, at the very end, we have this part of our graph, which is a triangle defined by the graph itself, the x-axis, and then we'll just complete it by drawing a vertical line between that. So you can see we actually have 4 segments that we have to look at 4 unique or 4 areas. The area of this graph is given by 1/2 the base times the height. The base in this case is represented by the change in time, which is 8 seconds. The height of the graph is the reading off of our velocity scale, and that's 2 meters per second. So the first shape, the triangle on our graph, has an area of 8.0 meters. The second shape, this blue rectangle, is the area is found by taking the base times the height. In this case, the base is from 8 seconds to 12 seconds. So the base is 4.0 seconds. The height is 2.0 meters per second. So our shape has an area of 8.0 meters. And that represents the distance or displacement in that segment of the trip. The third shape is again a triangle, 1/2 the base times height. The base is 3 seconds. Sorry, the base is 3 seconds. And the height is 2 meters per second. So we get an area of 3.0 meters for the third shape. And finally, for the fourth shape, I'll save myself a little bit of time and recognize that it's got the same area as the black triangle, but in the negative side, or in the negative coordinate system, the negative part of the graph. So it's minus 3.0 meters is the area of that shape. Now, to put these together as a total distance and displacement for the trip, we simply have to remember what the difference between distance and displacement is. Remember, distance is the total amount of travel distance, I guess, as long as we don't consider the direction. It's a scalar quantity. It's the sum total of all the distances traveled through the trip. In order to calculate that, we will take our distance in the first part, 8 meters. So we'll write that. Didn't give myself quite enough room, but let me just go back and do this. So we had 8.0 meters because of the first part of the trip. We had 8.0 meters because of the second part of the trip. The third part of the trip was 3.0 meters, and the fourth part was also 3.0 meters. Remember, it is negative, but we're talking about distance here. So when we put it together, we only worry about the magnitude of that. So we have 8 and 8 is 16, and 6 is 22 meters is our distance traveled. On the other hand, displacement does have to consider the direction. So while the first area was 8.0 meters, and the second area is 8.0 meters, and the third area was 3.0 meters, just like with distance, it's that fourth segment of the trip where we have to indicate the direction. It's minus 3.0 meters. So when we add this all up, we get a total of 16.0 meters as the distance, sorry, the displacement traveled. Let's move along and see how we can use a velocity time graph to calculate the acceleration. In this case, we have 3 segments, the first, the second, and the third segment in terms of changing velocities. So by definition, acceleration is the change or the rate of change of velocity. What that means is, whenever we ask about acceleration on a velocity time graph, we're looking at the slope. For example, if we want to find the acceleration from a time equal to 0 to a time of 8 seconds, this first segment here, then we just ask ourselves about the slope during that period of time. So from time equal to 0 to time equal to 8 seconds, the slope is equal to, well, your math teacher will say rise over run, but what we're really looking at is the change in velocity over the change in time. So the change in velocity for that period of time, starting at 0, going to 2, so this represents a change in velocity equal to 2 meters per second. So 2.0 meters per second is our change in velocity, and our change in time is represented by how far we run along the x-axis, and that is 8.0 seconds. So 8.0 seconds, and we get 2 divided by 8 is 1/4, or 0.25 meters per second squared as our acceleration. If we do a similar analysis of the last segment, you'll notice that we can treat it as one segment here because it's just one continuous slope. So from this time of 12 seconds to this time of 18 seconds, we have a rise, which actually is not even a rise, it's a drop. And it goes down from here, that's down 2 meters, and down another couple of meters here. So we have a total drop down here of minus 4.0 meters per second. And we have a run from the 12-second mark all the way over to the 16-second mark, so that's a run of 4.0. So when we calculate the slope for this region, the slope or the acceleration is delta V over delta T. We get minus 4.0 meters per second over 4 seconds, or minus 1.0 meters per second squared. So again, for any segment of our graph that has a consistent slope, we can simply find the slope of that graph to find the acceleration.